Hello students, today we are going to discuss about the simple stress and strain. Stress and strain. So first of all, we will take the introduction of the stress and strain. In, in engineering mechanics, we have discussed about the effect of force. Then, but in this subject, we are going to discuss what is the effect of external forces on the internal changes in this mechanics of structure. So are you getting, I think you are you getting the difference between the engineering mechanics and uh, mechanics of structure. In engineering mechanics, what means the forces acting on the body that we have studied, but the effect of that forces on internal bodies that we have not considered. So in this in mechanics of structure, we are going to discuss what is the effect of external forces on the internal changes of the body. That is the major difference between the uh, engineering mechanics and mechanics of structure. So first of all, we'll start from the materials normally used for in the construction. That is cement, sand, brick, stone, steel, and concrete are the materials which are normally used in the construction industry. Mechanical properties of the structure. First of all, we're going to discuss about the strength. It is defined as the capacity of the material to which withstand load, and it is the ability to sustain the load up to the collapse or rupture. So here we have discussed about the distortion. So what do you mean by the distortion? If suppose here it is considered as a one plate, it is welded, and if if due to the load, if some loads are acting on this plate, then the plate will deflect, so it changes its shape. So these are some examples I have shown here. So this is a simple example of the distortion. The second figure is also buckling of the plate due to the external load. So here angular distortion I have shown here, longitudinal distortion here. These are the simple examples of the distortions. Materials are classified into the following categories: elastic material, plastic material, elastoplastic material, ductile material, and the brittle material. First of all, we are going to discuss about the elastic material. It is the material which undergoes deformation when subjected to the external force up to certain limit, such that the deformation disappears on the removal of the force, is nothing but the elastic material. The second one is the plastic material. It is the material which undergoes deformation when subjected to the external forces, such that the deformation does not disappear on the removal of the force. Then third material is elastoplastic material. As elastoplastic is a material which undergoes deformation when subjected to the external force, such that the deformation partially disappears on the removal of the force, is nothing but the elastoplastic material. And the next type of material is a ductile material. Ductile material, it is the material which allow itself to drawn out by tension to a smaller section, is nothing but the ductile material. The elasticity, it is a property of the material. It is the property of the material which undergoes deformation when subjected to the external force up to the certain limit, such that the deformation disappears on removal of the force. Then plasticity. A material is said to be plastic when it is subjected to the external load, showing changes in shape without destruction. Then ductility. It is the property of the material to undergo a considerable deformation under tension before failure. It is the ability of the material to be drawn into small section from a large section. Metal having elongation more than 15% are ductile. Then hardness. It is defined as the resistance of the material to stretch, wear, oblique penetration of its surface by harder bodies. Brittle material. A brittle material is a material in which no deformation takes place and it is fails by rupture when external force is applied is known as a brittle material. Then we will start from the stress. You know that stress, it is defined as the force resistance offered by the body against the deformation. Stress is denoted by the symbol sigma or small letter p. Let us consider this is the block. It is subjected to tensile force PT and PT on both the side equal in magnetic opposite direction, and we have taken a section at this point. Then if you have taken a section and if you want to keep this is first part of the section is in equilibrium, and this is the first part of the section and this one is the second part of the section. If you want to take a first part in equilibrium, then you know that if you try to draw the free body diagram of the first part, then you'll get this is the force that is PT. Now who will keep this part in equilibrium? That one is the internal resistance offered by this material against this external force. So this internal resistance will keep this first part is in equilibrium. Similarly, second part is bar also keep in equilibrium. So here stress is nothing but it is the ratio of force divided by the area, or you know that force is nothing but a resistance. From this figure, if this block is in equilibrium, then you will get that PT tensile force is equal to R. So PT we can replace by the R, or tensile force replaced by the internal resistance. In short, sigma is nothing but force upon area is nothing but resistance per unit area. Now the meanings of the various terms used in this formula, that is sigma is nothing but a stress and it is expressed in Newton per mm square. P is the external load applied, that is Newton or kilonewton, and R be the resistance, and A be the cross-sectional area perpendicular to the force or load in millimeter square or meter square. Then we're going to discuss about the types of stress. There are three types of stresses normally found. First, tensile stress, second one is the compressive stress, and third one is the shear stress. First of all, we are going to discuss about the tensile stress. If a member is subject to tensile force, then a tensile resistance will be developed in the member. Then the tensile stress is nothing but it is the free body diagram of first part and the second part. So by applying the conditions of equilibrium, we will get the tensile force equal to the resistance. So tensile force is equal to tensile stress is equal to tensile force divided by the cross-sectional area, or by mathematically we can write sigma T is equal to PT divided by A, or R divided by the A. Then second type of stress is a compressive stress, when a member is subjected to equal and opposite axial push so that the length of the member is get shortened. The stress induced at any cross section of the member is termed as a compressive stress, and it is denoted by the letter sigma T. So here a member subjected to compressive force, so at the first end PC indicate the compressive force, at the last end PC, so equal in magnitude opposite in the direction the force are applied. Then if you have taken a section XX, then this is the free body diagram of the section first part and the second part. So this internal resistance will keep the first part in equilibrium, and internal resistance will keep the second part is in equilibrium. In short, compressive stress is equal to compressive force divided by the cross-sectional area, or sigma C is equal to PC divided by A is equal to R divided by A. Then the third type of stress, that is the shear stress or transverse. It is also known as a transverse stress, and it is denoted by letter tau or Q. Two equal and opposite forces are acting tangentially across the resisting section. The result of such a tangential force tend to shear up across the section as shown in figure. The figure is shown on the next slide. So shear stress is nothing but the shear force upon shear area, or shear stress is replaced by tau or Q is equal to P divided by the cross-sectional area of the rivet. Shear resistance divided by the shear area, that is nothing but R divided by A is equal to P divided by A. So this is the bolt rivet connected by these two members which keep in equilibrium. If the tensile force is applied, this tensile force is applied on this member, then this total tensile force is transferred on this bolt and the bolt will fail here. Okay, so that's this force is acting tangential to the member but tangential to the cross section of the rivet. That's why the definition is written like this. So next one is a strain. You know that strain is defined as the ratio of change in length to the original length is known as a strain, and it is denoted by letter E or epsilon, and mathematically it is expressed as strain is equal to change in length divided by the original length. Mathematically it is expressed delta L by L. Then there are three types of strain normally found: tensile strain, compressive strain, and shear strain. So tensile strain, if the member is subjected to tensile force P, due to which there is a change in dimension of the member, that is increase in the length of the member, at the same time there is a decrease in the cross-sectional dimension, then the mathematical tensile strain is expressed as follows, that is tensile strain is equal to increase in the length divided by the original length is equal to change in length upon original length. So change in length is nothing but increase in length divided by the length. So this figure shows this is the original shape of the member which is subjected to the force P. After applying a tensile force, there is a change in length of the member is this. This is the change in length of the member and is written by letter delta L. So this increase in the length divided by the original length is nothing but the tensile strain. The next type of strain is compressive strain. If the member is subjected to the compressive force and then there is a decrease in the cross length of the member, the ratio decrease in the decrease to the ratio decrease in length to original length is known as compressive strain, and it is denoted by letter small suffix e. So this is the member which is subjected to the compressive force. This is the total length of the member up to this point. Then due to this compressive force, the member get compressed and this P force is transferred here. So this is the P force. So what happens here? There is a decrease in the length of the member up to this one. So this decrease in the length is denoted by letter delta L, and original length is L. If you have taken this ratio delta L by L, then you will get the compressive strain. Then third type of strain is shear strain. Let us consider a block A, B, C, D whose one bottom end is fixed and at top end a P force is applied. Let us consider the length, top length of the member is L and height of the member as a L. Now see what happens when this P force is applied tangentially towards right, then the member will deform and takes a new shape that is A dash, B dash, C D. Now see here what happens here, the A is going to be shifted to the point A dash, correct? Then B is going to be shifted at B dash. So there is a deformation of the top layer with amount delta L. So at the top layer a P force is applied, and due to that P force there is a lateral deformation. So lateral deformation divided by the distance of that layer from the reference point or fixed point, this ratio is nothing but the shear strain. Or in short we can write tan phi is equal to opposite side divided by the adjacent side, that I have written on the next slide. So here in short, shear strain is nothing but mathematically the shear strain is expressed as delta L by L, but this delta L is nothing but translation or deformation of a layer in the direction of the applied force divided by that distance of that layer from the fixed reference point is known as a shear strain. Okay, then we are going to discuss about the Hooke's law. When we are going to discuss about the Hooke's law, a significant relation between the stress and strain is given by the Hooke's law, which state that stress is proportional to the strain as long as the material behave elastically. We have to mention previously that the property of the material regain its shape on the removal of the applied force is known as elasticity. A few materials shows elastic properties till they have attained considerable stress, while other material shows sign of such a property only for few small values of the stress. So this is about the Hooke's law. In short, Hooke's law is applicable up in the elastic limit. Okay, so in the next slide and in the next video, we're going to discuss about the Hooke's law and some numericals on this one. Thank you.